Hello, everyone. I hope everyone's doing well. And today we're actually going to start with a video. And this video is of 2 pennies in hydrochloric acid. So we have 2 pennies, and these aren't just 2 everyday pennies. Well, one is. One is a penny that is from post 1982. One is for a penny from pre 1982. Why am I talking about this? Well, in the 1980s, what people found out is that the price of copper, the amount of copper that goes in the penny, and because of the price of copper, the amount of copper that goes into a penny was actually worth more than a penny. So what you could do is you could take that penny, melt it down, sell it, and make money, right? So instead of making pennies out of pure copper, they actually now make pennies out of zinc, which is a much cheaper metal, and then they coat it in copper. So the penny on the left, you can't see, but that is from, I think, the somewhere in the 2000s. That is the newer penny. And the penny on the right is the pre-1982 penny. I have no idea where the date is, but let's take a look. And as we can see, only one of these pennies is going through a chemical change. You see the little bubbles on the left one. So the little bubbles on the left one, that indicates that there is a gas being formed. And when you mix a solid and a liquid and you produce gas, right, that is a unpredictable change. That's a classic example of a chemical change. And it's going to keep on bubbling. And we can see that none of those bubbles are coming from the right penny. They're only coming from the leftmost penny, right? So only one of these pennies chemically reacted, and that has to do with, obviously, the metal inside them. Let's talk about that. That's actually a quote from a YouTube group that I like watching. Let's talk about that. So, hold on one sec. I will be right there. Sorry about the wait. So let me write down our 2 reactions. The first reaction, and this was the one that actually happened. Actually, let's back up for a second. So we have this term called spontaneous. And spontaneous doesn't mean quick. Spontaneous means without the constant addition of energy. So spontaneous chemical reaction is one that keeps on going and going and going without constantly needing to add more energy into this chemical reaction. Whereas non-spontaneous is where you do need to add it. So theoretically, I could make both pennies react, just only one of them was spontaneous. Let's take a look at these 2. The first one I'm going to write, and I'll do that in blue, that's the spontaneous reaction. So we have zinc plus HCl, and that is producing H2 gas and zinc chloride. And remember that zinc has a +2 and Cl has a -1. So it would be ZnCl2 from the crisscross plus Hofbrinkel H2. And then we have to balance this. We have to throw a 2 there, and we're all balanced. And we said that this one's the spontaneous one. So I'm going to just give it a little S for spontaneous. And our next reaction, just copper plus HCl, and that's the copper +2. So once again, CuCl2 plus H2, and we need a 2 there. And this is the non-spontaneous one. Now, we can see these are both single replacement reactions, right? So that's what we're going to be focusing on, why single replacement reactions are spontaneous. And to understand why single replacement reactions are spontaneous, what we have to do is we have to look at exactly what is changing here, exactly where the electrons are changing. We can see that we're making a bond and breaking a bond, but what I want to do is I want to give the charges for each of these. Now, this is super confusing because we typically don't give H a charge. But for today, let's pretend H is a metal. And the reason that we're allowed to do that is because it is a group 1, so it has chemical properties that are similar to metals, even though it's a non-metal. So assuming H is a metal, we can see here that Zn on the top would have a charge of, when it's by itself, we remember they're neutral. H is going to have a charge of +1. Cl is going to have a charge of -1. That's in the reactants. For the products, Zn is going to have a charge of +2. Cl is going to have a charge of -1 times 2. And H2, we once again, 0. Right? Let's look at the bottom reaction. Copper by itself, and the element itself is 0. Same thing, we have a +1, a -1. We have a +2 and a -1 times 2. And then we have a 0. So we can see that in the top reaction, we have Zn0 donating electrons. And who are they donating electrons? How do I know they're donating electrons? Because we look in the reactants, it has a charge of nothing. It's neutrally charged. In the products, it has a charge of +2. To go from 0 to +2, you must have given out electrons. And let's look to see what's gaining. Well, Cl- goes to Cl-, so Cl doesn't change here. So the H+ is going from +1 to 0. Hey, that's gaining an electron, right? To go from +1 to 0, it's gaining electrons. So Zn- is donating electrons to H +1. And the way we would say that, the correct way we would say that, is that the Zn neutral species is donating its electrons to the H +1 species. That's in the top one, right? And then in the bottom one, we can say that, once again, Cu, you notice that Cu neutral is going to Cu +2, so it must be losing electrons. H+ is gaining electrons, so we can say that the Cu neutral species is donating electrons to the H +1 species, right? And the reason I'm bringing this up is because we know that metals lose electrons to become chemically stable. But this is weird because only one of these metals is actually losing electrons spontaneously. The zinc up here, the spontaneous reaction, is the only one losing electrons spontaneously. That means the copper over here, the copper neutral down here, is trying to give its electrons to hydrogen, a nonmetal, and it can't even do that. Isn't that crazy? And that all has to do with a very special, the reason that this all happens, the reason for the spontaneity has to do with a very special term called activity. So, single replacement reactions are based, spontaneity of single replacement reactions is based on this idea of activity. And it's very important that it's, remember, it's activity. This is not reactivity. And what I mean by that is activity and reactivity are not the same things. Remember that for the group 1, the most reactive metal was at the very bottom of group 1. That's francium or cesium, depending on if we're talking about actual or theoretical. This a little bit different. And let's take a look at table J. Here it is. This is table J. And as we can see over here, here's the most active metal, and then it goes all the way down to the least active metal. So what I want to do is look at my two reactions. And I will even highlight them for you. And in my first reaction, we have Zn and H as our metals, quote unquote metals. And let's find them. Here's Zn. And look at that, here's H2. And what do you notice? For our spontaneous reaction, we have Zn, a more active metal, acting like the metal. Zn, the more active metal, is donating the electrons in our spontaneous reaction. Okay? Just in case you weren't clear, see, Zn, more active, donating to H. In our bottom reaction, we said we had Cu. Let's find Cu on here. So let's erase all of this. In our non-spontaneous reaction, we have H2 again, but Cu is right below it. And look at that. For a non-spontaneous reaction, we have a less active metal donating its electrons. So that's how this works. That if a more active metal is acting like a metal in the reaction, the single replacement reaction is spontaneous. And let's do some practice there to show how that works. So what we're going to do is we're going to look at, I'm going to give you two reactants. We're going to predict the products, and then we're going to decide if it's spontaneous. So our first example, we would have FeCl2 plus K yielding. Okay, so we know to start with FCl2 has a minus charge. That's times 2. We know that, therefore, this is plus 2, and K is neutral. Single replacement. K forms a +1 ion, so when we crisscross it, remember crisscross comes before balancing, we get KCl plus Fe plus minus neutral. And then we need to balance it. We throw a 2 there, we throw a 2 there. It's all balanced. So let's see. What's acting like a metal here? Well, K is going from, I can write that down, K is going from neutral into +1. So that is donating an electron. Cl is going from -1 into Cl -1. It's not changing. Fe is going from +2 in the reactants to Fe neutral in the products. So therefore it is gaining an electron. So that Fe +2 is acting like the nonmetal. So K is the one acting like the metal. We have to double check. If the more active metal is acting like a metal, then it's spontaneous. So we have to check to see if K is more active than Fe. Let's take a look. Let's see. We have K over here. And assuming, since there's no K, Fe is not above it, I'm going to say it's yes. Fe is all the way down here. So K is more active than Fe. This reaction is spontaneous. Yay, let's do one more. Actually, I'm going to do 2 more, but this next one's special. Here we go. NaBr plus Cl2. No, I'm sorry. I2 yields. Okay, this is a single replacement reaction, but it's special. Why is it special? Well, in a single replacement reaction, before we had a compound reacting with a metal. Now we have it reacting with a nonmetal. And we know that Na is plus, we know Br is minus, and we know that I2 is neutral, but it's going to form a minus, right? So it can't bond. The iodine here, the I2, can't bond with the Br because it forms an anion, so it has to bond with the Na. And that's okay. NaI plus Br2. And then we just need to balance 2, 2. And I'm also going to find charges. We know there's a plus. That's a minus. Now, let's take a look at what's going on here. We have Na plus going to Na plus. Uh-oh. Nothing happens. Okay. Br minus going to Br neutral. So that looks like it is losing an electron. And then we have I neutral going to I minus. That looks like it's gaining an electron. So before we said that if the more active metal is acting like a metal, then the single replacement reaction is spontaneous. We have a problem here. Problem number 1. 2 problems, actually. Na is the only metal here, and it's not doing anything. Problem number 2. And I'm sure all of you are screaming the right answer right now. But if we look at this whole list right here of metals, you won't find iodine nor bromine. But hopefully you notice this list up here, right? Now, metals tend to lose electrons, right? So when a more active metal is acting like a metal, spontaneous. Over here, we have 2 nonmetals, but it still works the same way in that if the more active non-metal is acting like the non-metal, it is spontaneous. The reaction is spontaneous. So let's check it out. Over here, we see that Br is more active than I. So let's see what's going on in our reaction. Br losing an electron, I gaining an electron. Uh-oh, I is the one acting, I neutral is the one acting like the nonmetal. So this reaction would be non-spontaneous because the less active nonmetal is acting like the nonmetal. Non-spontaneous. Okay. Do we have time? We do have time. Let's do one more practice. And I'm doing this one with a polyatomic ion. TiSO4 plus H2 yields, it's a little bit confusing, but the polyatomic ion, now when I calculate the charges, I look at the whole thing. -2, this is +2, and this is neutral. Now H, remember, we're pretending it acts for single replacement reactions. H is going to be metallic-like, so it forms a +1. So if we have H of +1, SO4 of -2, -2, we do a crisscross to get H2SO4, which is going to be over here, plus Ti neutral. And it's all balanced out. Yay! So we know that this is the H is +1 times 2. The SO4 is -2. And this is neutral. So let's look at it. I can see that the SO4 isn't changing at all. That just leaves Ti and H2. Ti is going from +2, species of +2, to Ti neutral. whereas the H neutral is going to the H plus 1. So over here, Ti we can see is losing or donating an electron, whereas H is gaining an electron. So we see that Ti is the element acting like the metal. Let's find them on the periodic, the table J, the activity series table. We have Ti right here. We have H2 over here. So Ti is more active. If Ti is more active and it is acting like the metal, that makes this reaction spontaneous. Okay, and we'll get more practice in class. Thank you for watching. I hope everyone has a good day. Bye.